Hello, everyone. Welcome back to another lecture of Geometry of Mathematical Physics. Before we move on to the formulation of non-abelian gauge theories next week, today I'll discuss a few more aspects of abelian gauge theories, which will have a generalization to the non-abelian theories that we'll study later. So I'll start by returning to the concept of gauge symmetry, or rather, I should say, as I discussed last time, gauge redundancy, and discuss the idea of gauge fixing, which is how to get rid of this redundancy in the description of the theory. So I'll start again with the Lagrangian density, or in brief, Lagrangian 5.4 that I wrote last time, which involved a scalar field of charge 1 subject to a U1 invariant potential and coupled to a gauge field, a mu, through the covariant derivative here. And the gauge field has a called Maxwell kinetic term. And we call this theory scalar electrodynamics. And here, let me make a couple of remarks. So first of all, f mu nu squared is a shorthand for f mu nu. D mu phi absolute value squared is a shorthand for d mu phi bar d mu phi, where repeated indices are summed over. And this is the Lagrangian that I set last time. And after writing the lecture notes for last time and starting to prepare the lecture notes for this time, I noticed that Andreas in the first term used a Minkowski metric with the minus sign in front of the time component, the 0, 0 component, and plus sign in front of the spatial components. And in that convention, I should put a minus sign here in front of the kinetic term to make sure that the time derivatives squared appear with a positive sign. So I've corrected the formulas of the previous lecture accordingly in the lecture notes. So we'll stick to this version of 5.4 later on. And I'll also sometimes denote the potential as V of phi bar, which takes the form written above when we impose U1 symmetry. Okay, we have this Lagrangian density, and then we can find the equation of motion, which I'll denote as EOM. And these are nothing but Euler-Lagrange equations. There will be two types of equations of motion. One is the equation of motion for phi. The equation of motion for phi bar can be obtained by complex conjugation. The equation of motion for phi is d mu, where d is the covariant derivative of phi, is equal to minus partial derivative of v, the scalar potential with respect to phi bar, which, when I use the constraint of gauge invariant, is simply the derivative of capital U with respect to its argument. So that's U prime times the derivative of absolute value of phi squared with respect to phi bar, which is phi. And similarly, there is an Euler-Lagrange equation for the gauge field, which is simply partial derivative with respect to x mu of f mu nu is equal to g squared j mu, not the capital J here, where capital J mu is I phi bar covariant derivative d mu of phi minus phi covariant derivative d mu of phi bar, which is equal to the conserved current of the theory with the U1 global symmetry, small j mu. That involved ordinary derivatives, but now there are the covariant derivatives, so there is a correction term, which is plus 2 a mu absolute value of phi squared. And this is the conserved current of the gauge theory. I'll leave the proof of this as an exercise. This is exercise 5 in the problem sheet. It's just a matter of applying Euler-Lagrange equations and then checking the conservation of current. Okay, let's think now about the equations of motions in 5.14 a little better. And in particular, let's consider what happens when we perform a gauge transformation. Under U1 gauge transformation, (5.6), the equations of motion transform as follows. The first equation, equation 1, for the scalar field, so phi transforms covariantly, has charge 1, the derivatives d mu are covariant, and so the left-hand side, and the same also applies to the right-hand side, in fact, transform covariantly, like a field of charge 1, and so in particular, they will be multiplied by e to the I alpha if we perform a gauge transformation. On the other hand, in the second equation, well, the left-hand side is clearly gauge invariant because F mu nu, the field strength, is gauge invariant, and J mu, therefore, must also be gauge invariant in order for the equation to make sense. And I invite you to check that using this definition of J mu. So the equation for phi is gauge covariant, and the equation for A mu is gauge invariant. What this means is that if a field configuration for the scalar field phi and the gauge field A mu solves the equation of motion 5.14 that I wrote up here, then the gauge transformed fields phi prime, which is e to the I alpha phi, and A mu prime, which is A mu plus d mu alpha, also solve the same equations of motion 5.14. But this means that the equations of motion only determine the fields phi and A mu up to a gauge transformation. And in particular, suppose that we're given initial data specifying the value of the field, the scalar field phi, and the gauge field at an initial time t naught. Then, because of the previous comment, we cannot uniquely determine the values of the gauge field and the charge scalar field phi and A mu at a later time, t larger than t naught, because the gauge transformed field phi prime and A mu prime provide as good a solution as the configuration phi A mu, and also obeys the same initial conditions at time t 0. Provided that the gauge parameter alpha is 0 at time t0. This seems problematic at first sight because we would like the equations of motion to define a well-posed initial value problem which determines uniquely the physical configuration of the system at later times given the initial condition. This does not work if we treat the values of the charge scalar field and of the gauge field as physical. And in fact, in order for the initial value problem to be well posed, this requires us to identify field configurations which are related by a gauge transformation. If we do that, then the previous problem that the equation of motion doesn't really determine the time evolution of the field configuration dissolves, because the problem is only to do with the field configurations which differ by a gauge transformation. But if we now identify field configurations which differ by a gauge transformation, and we say that those correspond to the same physical configuration, then the problem goes away. And the consequence of this is that physically observable quantities must be gauge invariant. For example, in scalar electrodynamics, we could look at the field strength, F mu nu, or the conserved current, capital J mu, or say the absolute value squared of the scalar field, etc. Hopefully this explains remark number 3 that I made in the first lecture, this term. Now, to get to the ideal gauge fixing, let me first draw a picture which is useful to keep in mind. The following, so I'll start first with a picture and then I'll write words. So I'll start with this square, which denotes schematically field space, so the space of all field configurations consisting of, in our case, the complex scalar and the gauge field. And let me draw curves for field configurations which are related by gauge transformations. These are called gauge orbits. And in mathematical language, we would say that the picture is that field space F is foliated by gauge orbits Foliated is a mathematical term that let me not get into the definition. The point is that you can describe all of field space as the union of these gauge orbits, which do not intersect one another. And in particular, these gauge orbits for our case in the gauge group G, which is U1, is defined as follows. So we start from phi of x, a mu of x, say some field configuration that's a point in field space, say this point here, and then we act on it with the gauge group G, and we consider the set of all gauge transformed field configurations which are obtained by acting with the gauge group. So we get the set of all configurations e to the I alpha of x, phi of x, a mu of x plus d mu alpha of x, which are related to the original configuration phi of x, a mu of x, by a gauge transformation. And so in our case, for gauge group being U1, we know that alpha is a periodic function of space-time, so it's coordinate dependent. Okay, this is perhaps a bit abstract. So all it means is that in down-to-earth terms, a gauge orbit consists of all the field configurations which are related by a gauge transformation. And what we said earlier is that any two field configurations which differ by a gauge transformation should be physically identified. And this means that really a physical configuration does not correspond to a field configuration of the gauge variant scalar field phi of x and the gauge field a mu, but rather it corresponds to a gauge orbit. Rather than working with this redundant description of field space, sometimes it's useful to fix a gauge, or sometimes I'll say pick a gauge. That is, pick a single representative for each gauge orbit. So any representative is good because after all, they're all physically equivalent, but we need to make sure, ideally, that we cut each gauge orbit exactly once. So you'd like to have a picture perhaps like this, say that this could be my gauge fixing. So for each of the orbits that I've drawn, I would select, if that is my gauge fixing, I would select these representatives. Okay, what does this mean in practice? Well, let's look at a couple of examples of gauge fixing. The first example of a gauge fixing is the so-called Lorentz gauge. in which we impose the constraint that a mu as a Four vector is divergence free. And this can always be achieved. Indeed, suppose we're given a representative of a gauge orbit such that the a mu is different from 0. So we're outside the Lorentz gauge. Then we can find another representative of the same gauge orbit a prime mu. So it's in the same gauge orbit, which means that it's related to a mu by a gauge transformation, such that this new representative obeys the Lorentz gauge constraint. So why can we always do that? Well, the reason is that I can use the definition of a prime mu that's related to a mu by the gauge transformation. So I get the for divergence of a mu plus d mu alpha. And we can always arrange this to be 0 by picking alpha to solve the equation box alpha, d mu alpha equal minus d mu a mu. This equation always has solution, so we can arrange for a gauge field to be in the Lorentz gauge 5.17. Okay, now let me briefly discuss an advantage and the disadvantage of the Lorentz gauge. So the advantage is that the Lorentz gauge is Lorentz invariant. And note, by the way, that the Lorentz of special relativity of Lorentz transformation is not the same Lorentz of the Lorentz gauge. They differ by a t. On the other hand, the disadvantage of the Lorentz gauge is that this is really an incomplete gauge fixing. So it doesn't single out a unique representative. And the reason is that we're still free to do gauge transformations. With the gauge parameter alpha, such that the mu alpha is equal to 0. And this will keep us in the Lorentz gauge. So the Lorentz gauge is nice Lorentz invariant, but it doesn't really fix a gauge uniquely. So this picture that I had up here, where the gauge fixing determined a single representative for each gauge orbit, actually doesn't apply to the Lorentz gauge. So one has to supplement this by further conditions. The second example is a so-called Coulomb or radiation gauge. Where here we impose a constraint that the 3-vector A is divergence 3. Now, let me start with the disadvantage of this gauge. The disadvantage is that this condition is not Lorentz covariant. So we start with a Lorentz invariant theory, and then we impose a condition on the gauge field, which is not Lorentz covariant, and then we lose all the power of Lorentz invariance. That's not ideal. On the other hand, an advantage of the Coulomb gauge is that the scalar gauge potential, which really is scalar only under rotation group, not under the Lorentz group, A naught is determined by the charge density rho, which is the temporal component of the conserved current, as follows. So A naught, which is a function of x and t, is determined essentially as in electrostatics by the following integral d3 x prime of rho, the charge density at x prime t over the distance of x minus x prime. And as an exercise, please determine the proportionality factor. And a hint for that, if you need it, but most likely you will have seen 5.21 earlier in mathematical physics or special relativity and electromagnetism. Anyway, the hint is to use the fact that 1 over x is a green function for the Laplacian, which means that Laplacian of 1 over x is 4 pi times a theta function in three-dimensional space. Anyway, this is a really side remark, so don't waste too much time on this exercise. So if we're in the Coulomb gauge, and if the charge density is 0, for instance, for pure electromagnetism, which means that there is no scalar field phi, we have that now the right-hand side of 5.21 vanishes, and therefore the temporal component of the gauge potential vanishes as well in Coulomb gauge. On the other hand, if there is charged matter, it's not true that A naught vanishes in the Coulomb gauge. This leads me to my final remark in this section about gauge fixing, which is also an exercise number 6, which I very much recommend. And the exercise has essentially 2 parts. So the first part is that we can always gauge fix, or in fact, this is again only a partial gauge fixing, but we can certainly use gauge redundancy to fix a gauge where A0, the temporal component of the gauge potential, vanishes. And the second part of this exercise is that in this gauge, it's easy to calculate the energy of scalar electrodynamics, which has the Lagrangian density that I wrote at the beginning of the lecture. And this energy is given by the following formula. It's an integral over space of the energy density or Hamiltonian density, which is the time derivative of phi, absolute value squared, plus the covariant derivative or the covariant gradient of phi. So these are derivatives and gauge fields in special components. Then we have the scalar potential U. And then we have a contribution from the gauge fields, which is simply 1/2 G squared times the sum of the modulo squares of the electric and the magnetic fields. So here EI is time derivative of AI, and BI is related to the special components of the field strength. All right, enough about gauge fixing, at least for now. In the remainder of today's lecture, I'll discuss U1 Wilson lines and Wilson loops briefly, and the relation to covariant derivatives. And this is really an appetizer of chapters 7 and 8. So we'll return to these notions and revisit them when we discuss the mathematical formalism that underpins gauge theories. To make the discussion concrete, let me start by recapitulating a fact that you saw last term, and I also reminded you of in the first lecture this term, namely that if phi is a gauge field, then its partial derivative d mu phi is not gauge covariant, so it doesn't transform nicely in a representation of the gauge group. And here I'll stick to phi with charge 1, but as an exercise you can work out what changes if phi has charge q. Okay, why is the partial derivative of a complex scalar of charge 1 not gauge covariant? Well, to understand this point better, apart from just doing the calculation and checking it, we can look at the total differential of phi. So phi is a function of multiple variables, and I remind you from calculus, you can define the total differential d phi of x, which I'll define as a limit, where we compare the value of phi at the infinitesimally close points, say x plus epsilon dx and x. And epsilon here is a keeping parameter that I take to 0 in the limit. And then if you Taylor expand the numerator, you just need to keep the linear order in epsilon. You take the limit, and you see that this is the partial derivative of phi in the x mu direction times dx mu, the infinitesimal increment in that direction, summed over mu. And now this, inside the limit, we have the difference of two terms. And the problem is that the two terms have different gauge transformations. Because they are defined at different points. So we have phi of x plus epsilon dx that will be multiplied by a phase e to I alpha of x plus epsilon dx. Whereas phi of x is multiplied by a phase which is e to the I alpha of x. And the problem is that these two phases are different. But luckily for us, this problem can be fixed by introducing the so-called Wilson line in physical parlance, and we'll learn later the mathematical parlance. One there talks about parallel transport, etc. So what is this Wilson line? So we start by defining a curve, say, which connects 2 points in space-time x1 and x2. Let the curve be C. Which we can parameterize by parameter tau. And the curve is a map, say, from an interval inside the real line to space-time, and it maps tau to a space-time point x mu of tau, such that, say, when tau is tau1, we get to x1, which is x of tau1, and x2 is x of tau2. And as tau increases from tau1 and tau2, we interpolate from x1 to x2 along the curve C. Okay, then given this curve, we can define the Wilson line in this case of charge 1 along the curve C is denoted by WC. The curve has two endpoints here, x1 and x2, so I'll denote this Wilson line as WC of x2, x1. And this is given by the exponential. We'll get to why we need an exponential later on, of I times the integral of a mu of x dx mu. So this is a differential, and we can integrate it along the curve C, say, which goes from x1 to x2. And in practice, what this means, if we use the parameterization above, is that this is the exponential of I integral over tau from tau1 to tau2, a mu of x of tau, x dot mu of tau. So this is the Wilson line associated to an open curve. Instead, if C is a closed curve, say x1 is equal to x2. So say it looks something like this. Then we denote this by WC, this exponential of I times the integral on a closed curve. That's the reason for the circle of a mu dx mu defined as above. This is called a Wilson loop because the curve now forms a loop in space, time. Again, it's a Wilson loop of charge 1. And in fact, it doesn't depend on x1 and x2 by results that you know from calculus. It only depends on the curve. Now we have a proposition which is that under U1 gauge transformation with parameter alpha of x, as in equation 5.6, the Wilson line WC of x2, x1 transforms as follows. So we get the Wilson line, and then it's multiplied by a phase, and I write the phase as e to the I alpha of x2 times e to the minus I alpha of x1. So here, for U1 gauge theory, everything commutes, so I could have put the two exponentials together, but as we'll see, this is suggestive of what happens later on when we study non-abelian gauge theory, so let me write it this way. All right, let's discuss the proof briefly. So we'll start with the Wilson line, which I remind you is exponential of I integral from x1 to x2 of a mu dx, where the integral a mu dx mu, where the integral is along the curve C. And under a gauge transformation, what happens is that the gauge field goes to its gauge transform a mu plus partial derivative of alpha with respect to x mu. And now we can split up the integral into two terms and then split up the exponential of the sum into the product of two exponentials. And so we'll get exponential of I integral of a mu dx mu from x1 to x2 along the curve C times exponential of I integral from x1 to x2 along curve C of the mu alpha dx mu. So now the first term is, the first factor is simply the original Wilson line. And for the second factor, we note that this is really a total derivative or an exact differential. And so we simply get contributions from the endpoint. So we get e to the I alpha of x2 minus alpha of x1. And this is the result, which I can also write in a suggestive form that we'll refer to later on when we look at non-abelian gauge theories like this. But really, this is just rewriting for abelian gauge theories. And while we're here, let me also mention a corollary. And the corollary is that the U1 Wilson loop is gauge invariant. And the reason is that the loop is closed, so it has no boundary, or in other terms, you could start and end at the same point, x1 equal to x2, and then the two phases cancel out. Okay, why is this proposition about the gauge transformation of the Wilson line useful or interesting? Well, let's consider the complex scalar phi at point x1 and multiply it by a Wilson line from x1 to x2 along the curve C. And now let's consider the gauge transformation of this object. Now the Wilson line transforms as above, so we get e to the I alpha of x2 times the Wilson line from x1 to x2 along curve C times e to the minus I alpha of x1. And then phi of x1 transforms into e to the I alpha of x1 times phi of x1. And so we see that we can cancel out two exponentials, and this is equal to the e to the I alpha x2 times the original expression, the Wilson line from x1 to x2 times the field at x1. So this product here has precisely the same gauge transformation as phi of x2. So if we go back to the beginning of this section, we had the problem when we looked at the gauge transformation of the total differential here, that the two terms that we were subtracting had the different gauge transformation. But now we can fix that by using the Wilson line. Now consider the covariant differential, or total, I should say, covariant differential. d phi of x with capital D, which is d mu phi of x dx mu. And now we define it similarly as a limit, but now we insert a Wilson line so that the two terms have the same gauge transformation. And say the Wilson line is along an infinitesimal curve DC. DC is an infinitesimal line element. Now we can Taylor expand everything in the numerator to first order. So we get that the Wilson line along the infinitesimal line element from x to x plus epsilon dx is given by exponential of I times the integral from x to x plus epsilon dx along the infinitesimal line element of a mu, say of x prime d x prime mu. Now, since the extent of a line element is infinitesimal, we can rewrite this as e to the I a mu of x times epsilon dx mu, the extent of the line element, plus order epsilon squared. And if I Taylor expand the exponential, I get 1 plus I epsilon a mu of x dx mu plus order epsilon squared. Okay, now let's substitute this back in 5.29 and multiply. We'll also have to Taylor expand phi of x plus epsilon dx. And we find the following expression for the gauge covariant differential. We'll have limit as epsilon goes to 0 of 1 over epsilon times phi of x plus epsilon dx. When we Taylor expand, becomes phi of x plus epsilon d mu phi of x dx mu plus order epsilon squared. And then we'll have, oops, sorry, here in 5.21, I was missing the phi of x here. Apologies. Now I have to multiply the Taylor expansion of the Wilson line, the infinitesimal Wilson line in 5.30 times phi of x. And so I get minus phi of x minus I epsilon a mu of x phi of x dx mu plus order epsilon squared. Now I can cancel equal and opposite terms. I can take the limit and I get the partial derivative of phi x with respect to x mu minus I times a mu of x, the gauge field, times phi of x. And all of this multiplies the x mu. And so we see that the definition of the gauge covariant differential in 5.29 reproduces precisely the definition of the gauge covariant derivative that we introduced earlier. Namely, that d mu phi is ordinary partial derivative minus I a mu times phi. All right, we'll see more, in fact, much more about this later when we study fiber bundles and sections. So let me just conclude with a couple of remarks that I'll just say in words. They also have to do with quantum mechanics, which is not a prerequisite of this course, but for those of you who are studying quantum mechanics, let me mention that in quantum mechanics, the Wilson line actually has some importance, and it's precisely the phase which is picked up by the wave function of a charged point particle, which moves slowly along the curve C in the presence of a gauge field. And likewise, the Wilson loop is important, and in fact, the Wilson loop is gauge invariant, and therefore it's physically observable. And in quantum mechanics, in fact, the Wilson loop is what controls the so-called Aharonov-Bohm effect, which is a very peculiar type of quantum interference due to the fact that a charged scalar couples to the gauge field directly and not just to the field strength. So even in situations in which the field strength F mu and therefore the electric and magnetic field are vanishing throughout all of the space that the quantum mechanical particle can probe, it turns out that if in this space there are some loops which are not contractible to a point, then you could have this phenomenon of quantum interference, which is the Aharonov-Bohm effect. So that's all for today. See you next week when we'll start to develop the formalism of non-abelian gauge theories. Bye.